Hi everyone, I'm Shen from Stony Brook University. Today I'm going to talk about our new work, Scalable Neural Dynamic Equivalence for Power Systems. This work is a pivotal component of our AI Grid project in collaboration with SO New England. Special thanks to all my team members for their help and their contributions. To begin with, why are we focusing on neural dynamic equivalence? Traditional power system analytics are normally model-based, which rely highly on accurate models. On one hand, contemporary power systems are increasingly intricate, incorporating renewable energy sources such as solar, hydro, wind at all levels. Obtaining such an equivalent model for offline analysis may be feasible. However, it presents limitations in terms of online analysis. The challenge arises from the fact that even if we can have an equivalent model, it is static and will not update itself. During our discussion with SO New England, we found that for utility or industry needs, they want to have an equivalent dynamic model instead of static model. That's why we are doing this work. For example, if we want to analyze the system in this figure in real time, but our EMS does not have access to the territory outside the green circle, the internal system, then everything on the outside is called the external system, which is not identified. Then the traditional model-driven approach cannot proceed. Not to mention the nonlinear dynamics and unforeseeable control modes. All of these factors, the challenges prompt us to explore AI techniques. And on the other hand, abundant continuous time data from advanced sensors are not fully exploited, like PMUs and SCADA. So we employ a data-driven dynamic equivalent model to discover the state space model of the unknown subsystem. First, it can harvest information from big data. And second, our utilization of ODE nets ensures the retention of the intrinsic continuous differential structure of the model, making it adaptable to various scenarios. And last, this dynamic model can update with corresponding results in real time if you including PMU measurements also in real time. Then why is this problem difficult? How is it difficult? The first challenge is that this neural network learns from data, but it needs to align with the physics at the same time. In this specific problem, our goal is to learn the state space model, not simply curve fitting or trajectory prediction. So we formulate the problem as an ordinary differential equation to represent its state space model. X here is the state variable from the external system. In this case, X is the current along the timeline. We will discuss this later. And U is the input from our internal system. X and U can easily be obtained from PMUs. N here represents the neural network. This formulation naturally leads to another challenge. That is, the ground truth measurements are discrete, while our outputs from the network are continuous. So we cannot directly get such a loss function to optimize the neural network. We can see the output is a derivative of the state variable with x dot, but the measurements only provides us with the state variable x itself, not the x dot, meaning that we don't have ground truth value for x dot, only for x. Here, how to proceed? We have two solutions. The first one is called discrete learning, and the second one is called continuous learning. In discrete learning, we can discretize the measurement x, then compare with the predicted derivatives. However, we found that it's very sensitive to the estimation of derivatives, which easily leads to biased training results because of the tiny residue error accumulated during the training process. While continuous learning integrates the derivative, then compare with the ground truth x. At the bottom, we show the necessity of continuous learning. You can see that on the left, the discrete time learning representative, DNN, the green dotted, the orange dotted line, and the purple line, our method, they both work well when predicting the derivatives, actually quite perfectly. However, on the right, in the closed loop test, you can see on the legend, the y-axis is the x, not x dot, meaning that this is the results after integration. We found the discrete time learning DNN is way off. And by saying closed loop, I mean we need to insert our equivalent model back to the known part. So the unknown part and the known part will interface and function and integrate as a whole part. This is the final step of the dynamic equivalence work. And we found that during the final step, DN will not work. Only our proposed method can work. Then how to implement neurodynamic equivalence? Like we mentioned before, the first one is the continuous learning. The continuous backpropagation of ODE-net is trained to best fit the continuous time behaviors according to the discrete time measurements, the discrete time inputs, let's say. Second, we incorporate physics into the training process as well. We can see that in the right figure, we show that during the training process, closed loop accuracy is included in the loss function, meaning that this interaction between the internal system and the external system is considered in every epoch during the whole training. This innovation guarantees accuracy in closed loop tests. And at the bottom is the whole training process. By inputting the measurement and deploying the adjoint method, which is very difficult. I did not put all the math derivations and equations here. Please refer to the paper for the complete equations. And finally, we can calculate the gradient descent. This ODE-net-based neural network can finally converge to a global minimum. To give a concrete example, consider a 140 bus MPCC system divided into two parts. The ISO New England system on the right is known, allowing for a direct modeling. In contrast, the left part, significantly larger, remains unknown, compelling us to rely on a neural network for the model acquisition. And the two subsystems are interconnected via two timelines. You can treat these two timelines as bridges, and those timelines are really important because for your external system, the only information you can access are from the measurements on the timelines. And this system is real. We cross-validate the results from our modeling, the MATLAB and Python modeling, with the ISO New England model in TSAT, and they're the same, they're identical. And in our results, as shown in the red figure, we simulate a short circuit fault occurring at bus 19 from 0.5 second to 0.56 second. Our equivalence results align quite closely, we can say perfectly with true measurements with mean error less than 0.05%. Also, choosing features of training is flexible. Other settings like using active and reactive power transmission lines, or you can use bus voltages or line currents, they are all feasible. As an example, figure 4a presents the testing result by using boundary voltages between external system and internal system and all branch currents as training features. And for the figure 4b uses boundary currents and voltages from all buses. The predicted trajectories match with the measurements quite well, with the mean error of less than 0.3%, indicating high accuracy and satisfactory performance of neurodynamic equivalence by different settings of training features. We also have a more extensive test results encompassing 108 scenarios with 16 different locations and random fault clearance times. This box plot gives an overall relative error of less than 1%, underscoring its remarkable accuracy. Furthermore, our method exhibits high adaptability to various fault scenarios like different locations, different fault durations. It shows superior generalization ability to new cases when compared to discrete time learning method like DNN I showed before. All those outcomes affirm the precision of our approach in capturing the dynamics of unknown subsystems. Next, I want to introduce the second part, is a practical application of neurodynamic equivalence of the driving port dynamic equivalence. In the previous slide, we have shown the physics-informed equivalence trains in a closed-loop manner by considering the interactions between the identified subsystem and the unidentified subsystem. To be honest, it suffers from heavy training. It made us wonder, can we be more practical? Can we use less input for more efficient training? We borrow some inspiration from the Norton equivalence theory, where we can imagine we see only from the driving port and view everything on the right as a black box to be learned by a neural network based only on the boundary voltage and Talon current, just like this. Then we employ a magical touch called algebraic component separation and enhance our ODE nets using recurrent neural network. And finally, we have these results with a comparable accuracy, but only 6% of inputs, significantly improving the efficiency. Then we're curious, if we only use 6% of inputs, can it be as generalizable as before? We don't think it's possible because you have so much less data, right? So we are curious about how to quantify the generalization ability. Therefore, we employ the electrical distance between the fault locations in the testing set and those in the training set as a measure. And this electrical distance is determined from the adjacent matrix by selecting the shortest distance. It can be observed from the figure 8 that when those electrical distances are relatively small, like 0.02, the generalization ability of this driving port equivalence is quite good. It's also worth mentioning that two oscillation modes with different frequency and magnitude have been predicted correctly as well. From table 1, we can tell for the same training set, the driving port equivalence is more efficient. The primary advantage of the driving port equivalence lies in its ability to perform dynamic equivalence even with limited features, let's say 6% of inputs as before. And this capability eliminates the requirement for extensive data acquisition and storage resources. However, we can tell that the increased training time for RNN-empowered deep driving port equivalence is notable. This is attributed to the inherently slow training speed of RNN compared to MLP. Another observation is that the driving port equivalence is not as satisfiable as a result from the physics-informed one. If the fault happens at a large electrical distance, let's say for fault 3, actually, if you take a closer look, the result is not as good as what we've shown in previous slides, the physics-informed one. Remember that in the previous slides, regardless of locations and fault durations, the physics-informed one can always have error rate of less than 1%. But the driving port equivalence is not. The reason behind this discrepancy lies in the training process, because the physics-informed equivalence trains in a closed-loop manner by considering the interacting dynamics of both internal system and external system, involving more than 50 dimensions of features. But the driving port one only sits from the driving port. It only utilizes 4 dimensions of features. far less. As a result, there exists a trade-off between training efficiency and generalization ability, which impacts the performance of the driving port equivalence for faults in distant areas. Even though the utilization of the RNN-empowered driving port equivalence can improve the generalization ability a little bit, further investigation is still required to address the time-consuming nature of the RNN training. To summarize, for faults not too distant from the training sets, both the driving port one and the physics-informed one can give satisfactory results. In case where a fault is significantly distant from the training set, the physics-informed one is better, and the driving port one is not as adequate, unless the training set can be expanded across a wider area. If your training set is bigger, then of course driving port can be better. But yeah, still there is a trade-off between your data set, your training, and the final accuracy. In conclusion, today I showcased a proposed method called neurodynamic equivalence, and I have two variants of it. The physics-informed one, which trains in a closed manner, but is more slow in training, and another one called the driving port equivalence, which only use a small set of features for the training, but is not as generalizable as the first one. And I have shown that both of the two methods can accurately capture the dynamics of the external system and give real-time predictions according to the online PMU data. For industrial applications, this equivalent work can update with real-time dynamics and makes online transient analysis and stability analysis possible. I believe the future of neurodynamic equivalence holds promise. We plan to implement it on a more complicated system with diversified testing cases. And we found some utilities already have their digital twins. So I think using AI on power system is a very promising area. And we will make it more efficient and scalable in larger scales. At last is the acknowledgement for the sponsorship from ASO New England, DOE, and NSF. And this is all for this paper. Thank you.